We looked at the general Euler's method for being able to approximate this numerical solution to a differential equation. Now let's take a look at something called the improved Euler method. Now the improved Euler method is a much more rigorous formula, and it's actually doing something called a forward difference. There's actually a backward difference sort of approximation of a derivative. But what this is going to do is it's going to use this formula, which is a pretty ugly formula as you can see, to be able to approximate the solution to a differential equation. And you might be asking, well, the Euler's method worked pretty good, and if I know how to use the original Euler's method with Excel, I could just go ahead and use Excel to compute very quickly, and that's absolutely true. However, as your step size gets smaller, the computation time to run it becomes more to be able to do that in general. So there are times where we want to be able to expedite the computation speed, especially if h is down around like the 10 to the negative 10th or something like that, if you need a really precise measurement for some reason. And so what this does is that it helps it to converge to the actual value much more quickly based on the value of h. Unfortunately, that does mean we'd have to do more algebraic steps for this. So let's do the exact same problem that we just did. And what we're going to do is we're going to use this improved Euler's method to be able to find the solution. And then we're going to go ahead and compare it to the original solution, the exact value. And you might remember that the differential that we're looking at is y prime is going to be equal to 4x minus 2y. All right, so for this one, let's just go through, and I'm going to show you the first two iterations just to make sure you guys know how to do it by hand if you ever needed to. And so here's what we're going to do. We're going to set up our table. So we have our iteration. Let's just do the first two, and then in the next video what I'll do is I'll show you how to utilize technology to be able to do this. Now remember, xn is just the given initial value, and you might recall that the initial value that we had, it was y at 0 is equal to 2. So we're going to have 0, and then this is our current y, which is 2. Alright, now here's the way I like to do this, and you don't have to do it this way if you don't like it, but what I like to do is I like to do the increments. So I like to figure this out first, then I also like to figure this part out as well. So this will be a column, and this will be a column as well. And then what we could do is we could just plug it all into the formula very nicely. All right, so first thing we need to do is just find f at xn, yn. So that's going to be our first column. All right, and for the first one, we know that's going to be 4 times 0 minus 2 times 2. Or in other words, that's negative 4. All right, so that's nice and easy. All right. Now, the next thing I like to do is I like to be able to find this yn plus hf at xn yn. All right, and that's the value that we're going to stick back into the formula. It's going to make it pretty easy for us to do. Now we know what yn is. It's 2. We know the step size is 0.1. And the good news is we already know what f at xn yn is. That's just the previous column. So that's going to be negative 4. Or in other words, that's just going to turn into 2 plus negative 0.4, which is 1.6, which is actually Euler's formula from before. All right, so we're actually using part of Euler's formula, but we do have to reuse it in this forward difference formula. All right. Now, unfortunately, I don't have enough room here, so what I'm going to do is I'm just going to go down here and recreate a table. So we have 0, 1, 2, and if you have enough room on your paper, what you probably want to do is you just want to have a y at n plus 1. So now we're just going to go ahead and find the next y. All right. So our formula says that we're going to take the current y value, and then we're going to add to it h over 2. So yn, the current y, is 2 plus 0.1 over 2. All right, and that just abbreviates it a little bit so we don't have to worry about it. We have f at xn, yn, which is negative 4, which we just found, plus, now here's the tricky part, f at the next x value. All right, so we're going to plug in, remember our x values are 0.1, 0.2, etc. And that's the forward difference that we're utilizing. So basically what we're doing is we're assuming that we already know what the next x value is, and we already do. It's just that we usually don't use it. All right, so I'm going to stick that back into our formula. So that's going to be 4 plus 2 times 0.1, or excuse me, 4 times 0.1. And then we're going to substitute back in for y. We're going to substitute the value that we just got, the 1.6. Okay, so we're going to say minus 2 times 1.6. All right. And now what we could do is we could just go ahead and compute this. All right, so if you'll just bear with me just for a moment, I can go through and figure this out in my calculator. All right, and I got 1.66. I did it beforehand. All right. Now, if I want to get to the next iteration, what I'm going to do is now the current iteration for y is 1.66. And now I'm just going to do everything over again. So 4 times 0.1 minus 2 times 1.66. All right. And that's going to give us a negative 2.92. That's a 6. So, and that's negative. And now what we're going to do is we're just going to substitute the current y, which is 1.66, plus the step size 0.1, times what we just got, the negative 2.92, and that's going to be equal to our 1.368. And then finally, we're just going to take that value and we're going to substitute everything back in. So the current y is 1.66, 0.1 over 2. Instead of negative 4, we're going to substitute this negative 2.92 plus 4 times the next x, which is 0.2, minus 2 times whatever we just got for yn plus h, etc. And so that's going to be this 1.368. And what do we end up with this time? We end up with 1.414. All right, now we could keep doing this, and I will do this again in the next video with the Excel. But let's just compare the values for the exact numbers. All right, now you might remember y at 0.1. So this is the approximation for y at 0.1, and this is the approximation for y at 0.2. So let's get the exact values. Okay, so these are the exact from the function. Okay, so remember the function we got was y equals 2x minus 1 plus 3 over e to the 2x. That was the exact analytic solution. And you might remember for the first one, we got approximately, excuse me, let me erase that so it actually looks like a real approximate, not just 2 lines. But we got 1.656 for the exact value. All right. Now, y at 0.2 for the exact value, and I know it says exact and I'm approximating it, but just assume that I'm plugging 0.2 in here to get to the analytic solution. And when I did that, I ended up with 1.411. All right, now how good is that? Well, check it out. We got 1.414 using the improved Euler method. And you can imagine that this is a fraction of a percent in error. All right, so this is the real value, is that we can finally see how good of an approximation the improved Euler method gives you. Now, I'm going to stop the video here, and what I'm going to do in the next video is I'm going to use Excel to be able to perform these rote computations very quickly, and then just like we did before, maybe we can play with the step size and see how powerful that changing the step size is, making it smaller, can be to getting us an exact solution.